morning, everyone, and welcome to the two-phase liquid immersion cooling masterclass presented by The Edge, TMGcore's content creation organization. I'm Drew Knoll, Vice President of Global Sales Ops and Development here at TMGcore, and will be your host and moderator for this morning's event. We're pleased and honored to have so many of you joining us this morning, and we're confident that this time will be both educational and inspiring for you all. We're privileged to have TMGcore CEO J.D. Enright live in his home studio with us to present what we believe will be the start of many fruitful and meaningful conversations around the evolution of IT cooling with specific respect to two-phase liquid immersion cooling. So with that, I will turn both the floor and the camera over to JD.
Hello and welcome from the Enright studio here in Texas. I have today with me my daughter, Nicole.
Hi, guys.
My son, John-David.
Hello.
And my cousin, Yvette. No,
Hi, everybody.
she's actually my wife, but you never know in Texas. So thank you for joining so much. Today, because we would normally do this in our Plano facility, which is a state-of-the-art facility where we have a studio, but because we're trying to be good citizens and keep you safe as well as us safe, we're doing it from the Enright home today. So we made this studio today. We are broadcasting live, so if things mess up dramatically, it's their fault because they're working behind the scenes to help me make this happen. No, just kidding. But bear with us. This is live, and our job is to educate you and have some fun along the way. So thanks, guys. If we can let them go so they can do all the magic behind the scenes. So first of all, you're probably wondering why I'm wearing this. Well, you know, we're dealing with very, very dangerous. I'm just kidding. We don't need any of this, actually.
This is not necessary. This is absolutely not necessary for what we're doing today. This stuff here, just not needed. In fact, don't need this either. This is just, you know, me making a point. And that point is two-phase liquid immersion cooling, like many other technologies in the industry, is extremely safe. That's right. So we're going to dispel a bunch of myths today that we don't need a lot of this stuff. Now, having PPE is important, like in any job, and knowing what PPE you need for what application is important. So don't go doing things that you shouldn't be doing without the proper PPE. I need my glasses here. So thank you for joining us today. The first thing I want to say is I hope all of you are feeling well, and on behalf of all of us at TMGcore, I'd like to express our sincere hopes that all of you, your colleagues, your friends, families, and loved ones are staying safe during this COVID-19 pandemic. We, like you, want things to get back to normal as soon as prudently possible. So we're going to give you an overview, a very high-level Disney overview of two-phase liquid immersion cooling. And we will have additional master classes through the Edge and the WebEx series, where we'll get into a lot of detail on technology, different aspects of the technology, and other technologies in the industry that are designed for cooling infrastructures for high-performance computing, like two-phase liquid immersion cooling. But for today, we're going to give you a very high-level overview of that. But let's start with the history first. Why have we gotten to this point? So we're going to be talking about, you know, what it is, why it is, how it's done, and the benefits, and some of the things that aren't so beneficial towards this and some of the similar technologies. So, so dating back all the way to, say, the 1800s, it's actually about, I believe it was 1893, vacuum tubes were invented. And those of you who are old as like myself, older, remember vacuum tubes, televisions and transistor radios, things like that. Then in the 1950s came integrated circuits, ICs, which was a quantum leap from vacuum tubes, although these days they're actually going back to vacuum tubes for some applications because they work really well. But for high performance computing, not so much. Then Intel came up with the microprocessor in the 1960s, which was a phenomenal thing. And the microprocessor is still going strong to this day. So we're going to be talking about the background initially on power, what we call power dissipation and cooling. And it would be a mistake not to talk about Moore's law. So Moore's law, where did it come from? You hear people talk about it all the time. So Moore's law was a concept, an idea. It was established by Dr. Gordon Moore. He was the founder of Intel, actually. And what he said was, his theory was around Moore's law was that densities, transistor densities, will double every 18 months, beginning in the 1970s. Guess what? History has proven this to be accurate, in particular in the microprocessing industry. So for example, let me give you one example in the telecom industry, which is part of the overall industry that we're in. What we call the heat flux increase jumped in just a 10-year span from 0.5 watts per cubic centimeter to more than 10 watts per cubic centimeter. That's a factor of 20. That means it's less than 18 months. So he was right. And in fact, it's accelerating even faster than that. So the chip and component junction temperatures are increasing in line with this massive increase in silicon performance and server densities. So what does that mean? Well, how do we address that? Well, historically, we did it through convection initially, just letting nature do its thing and remove the heat and blowing fans and things like that. And then we quickly got to densities where that just didn't work anymore, right? So what we had to do was do something where we had, we put heat sinks in place. We started putting cooling towers in place and refrigeration systems and chilling units. Things like that I have here today. We're going to be looking at a number of things, some of the things that are used today, some of the things that we're using in two-phase of immersion cooling, some of the things we've developed with our partners and so on. We'll be talking about that. And before I move on, I just want to say thank you and a big kudos. This is in part or in whole. We exist because of our partnerships and our collaborations with companies like Intel and Dell and Supermicro and HP and IBM and others, and companies like 3M and Solvay, who are tremendous innovators in their industry. And none of this would exist, inclusive of two-phase of immersion cooling, if it weren't for people like that. So thank you. Some of you, I think, are tuning in today. I hope this is, well, this is probably a little sophomore for you guys, but I'm sure you'll enjoy it, and I hope I can add some value. So thank you for joining us, and thank you for your partnerships. So some of the things are like heat sinks, for example. So this is a modern heat sink, very beautifully made and well-designed and engineered heat sink. This happens to be a heat sink for a GPU, something like that. What you see behind me here. This happens to be a Dell C4140 that's been converted into, or in the process of actually being converted to, what we call an Otto-ready server, which is used in the two-phase of immersion cooling industry, specifically in our Otto technology, which is two-phase of immersion cooling. So there's a number of things that aren't on here right now that would make it what we call Otto-ready or immersion-ready. But this is the Dell C4140. It's about 2,200 watts. We can overclock that in immersion much higher than that. But what happens is, typically what you'd have is you'd put, these are actually Tesla V100 GPUs. You would take a large heat sink like this, and you've got some material on the back here, which allows for good contact, heat contact, and you would put that on top there. This actually one comes off of an NVIDIA 4U server, a very powerful server, fantastic product. But what we did was we took them all off, and we figured out how to do it in immersion. But this here is a heat sink, and it's one of many different types of heat sinks. It's made from aluminum fins. There's some really nice copper in here, because copper is a really good conductor. And that would sit on here. The heat would come up through the chip. You would affix this to the top of the GPU or CPU. They make them for CPUs as well. Anything that has to disperse the heat. And then you would put that in the server. And then you would use things like fans, like this, and or like these things here. These are fans, electronics. A lot of them are made in Japan. I think this one is made in China. Or things like this. This actually comes out of the same thing that this came out of, which is a great server, a 4U server made by Gigabyte. This is the fan bank on the front of the server. So it's this thick, obviously, 4Us, and about 7 inches, a little over 7 inches. And this is the fan bank that is used to blow air across the inside of the server. And obviously you'd want to make sure that the air is filtered, and in many cases it's cooled to a certain temperature, so that allows for the dry, cool air to run across, because you don't want moisture. So you want to condition the air to certain humidities, and you'd blow that air through the server. And then that air would go across the heat sink here, which is basically taking the heat away from the GPU or CPU, the chip, and then pushing it out. And then you have fans on the backside, which are drawing it out. And then depending on the size, how many GPUs have, you'd have a certain amount of heat sinks and a certain amount of fans. They would run at a certain speed and so on. And one of the things that's interesting about this is, one, you can get a lot of density. Not what we do in from a high performance computing density perspective, but as dense as you're going to get in air cooling, you can get with these things. These are phenomenal. However, something like this uses about 15% of the electricity that you need. So it makes it for very inefficient. These are as efficient as you're going to get, but still in the overall scheme of things, compared to some other types of technologies like liquid on chip, rotary heat exchange, single phase immersion and two phase immersion, these are a lot less efficient, but nevertheless have done a great job up until now. And then you'll have things like PSUs, so these PSUs convert the power from whatever you're feeding it, 415, 480, 208, 120, whatever it is, to typically DC power, like a 48 volt or 12 volt DC power. And these also have fans. You can see little fans there. I don't know if you can see that. There's fans there, and these rotate at high speeds. This is a 2400 watt, 94% efficient product. This is actually a great Dell product, fantastic, and actually designed to go into the Dell C4140. So I just pulled that out there because we don't actually need these. So you can tell we removed them because we don't need these. We use a separate system for that. So we use PSUs that are like something like that, very thin. This is a 10,000 watt PSU that we use in our two-phase immersion. I'll put that over here because we'll talk about that later. So and what we're doing is we're taking these compute chips and things like that. We're blowing air across them. So that's what we've done. So what's the next step? So one of the problems of this is efficiency, and also as you start increasing your densities or your compute power demands, you have size limitations, right? For example, these heat sinks, in order to remove that heat load, get very thick and big, and it creates a bigger footprint, which means more concrete and more floor space and more costs. And these are expensive things. And imagine, from an environmental perspective, the amount of energy required to, say, mine the aluminum and the copper and then truck it everywhere and then melt it down and convert it, and all of the energy it takes to ship it, and secondary packaging, primary packaging, and all the things that has to do with the environment. So, so some of the positive things about it is they work well, and they've been historically what we've gone to because we just had limitations as to what was available to us. And so they've worked really well. Now they've hit the wall. And again, getting back to Moore's law, right? So cost, size, efficiencies, how much energy are you using, what's going into your workload, the actual compute versus what's going into the cooling application. In some cases, you could be using 25% or more, and 40% in some cases, of the amount of electricity you're using towards cooling versus actually going to the compute. And so the more we can drive to the compute in a smaller amount of space at higher efficiencies, the better off we are. So that's what we're going to talk about in that sense. So unless the servers and data centers are located in a cold area, which maintains a very low temperature range year-round, they require some form of cooling system infrastructure. Typically, it's chilled water or cooling towers or hot aisle containment systems, all of that to help with the final heat rejection and conditioning. So no matter what you're talking about, whether it's single phase, two phase, water on chip, rear heat exchanger, traditional air cooled stuff, you're going to need some type of cooling infrastructure. So, in the cases with air, you have chillers, you have filtration systems, because one of the things you don't want to do is have a bunch of dust build up on this. So you need to filter the air. When you filter the air, you keep pressure drop across the filter, things like that. So, and if you get dust on here and on the chips, it basically likes to bake it on there, and you have basically a degradation in your thermal transfer. And so all of a sudden you have to ramp up the fans higher, you have to cool down the air more, or it fails. One of the fail safes they put in place now are, they put software in place for the BIOS to say if you see temperatures increase on the chips, they shut down, the server shuts down and things like that, versus burning up like in years ago, things would just melt. Now they've got great software, great engineers who are developing systems that prevent those things from happening. However, they do require the system to be shut down. So then we have liquid cooling. So that's the air cooling stuff, right? It's all of this stuff that you have here. It's the heat sinks, it's the PSUs with the fans, it's the fan banks, it's all of those things. And then you have liquid cooling. Now, liquid cooling, there's a number of types of liquid cooling. There's liquid on chip. Liquid on chip is really interesting, and it's become really popular. And there's some benefits, like anything, and then there's some things that aren't so beneficial about them. So basically, this is not a unit for a liquid on chip, but just as an example, you would take a cold plate like this, and it would have some intricate channels carved out on it, typically aluminum, some copper, whatever. That's not what this is. Again, this is a heat sink that we designed. It's one of our designs. But you would take that cold plate and you would put it on top of your, in this case, the GPU, or you'd put it on top of your CPU, and then you'd circulate cool water. And so you'd have a cool water circulation system. And if you have a large hyperscale deployment or whatever, on a rack level, you have multiple racks, you would have a secondary system that would circulate the fluid through the cold plate system, and you'd have a series of tubes coming in and out, supply and return. You'd want to monitor to make sure that as you heat up the workload on the chip, the water would circulate, increase circulation, or the temperature would be modulated to make sure that you don't overheat the chips. And it works really well. However, there's some downsides to it. The downsides to it is it's a lot of work. There's a lot of it's a very complicated system in some cases. They're making it better. It's getting less complicated. It's getting a little bit more mainstream. However, it's the significant costs. It's operator heavy, and there's a lot of things. But it has its place. All the things we're talking about today are great products, and they have their place in the world. And certain applications and deployments, it's perfect for that. And that's water on chip. And then you have rear door heat exchanger, which is basically a heat exchanger on the rear side of a rack. One of the best companies out there making those things is Vertiv. Vertiv makes a phenomenal rear door heat exchanger product. I recommend it if it's something that you're interested in deploying, and you can get some pretty significant densities. I think, in some cases, 50 kW per rack. I hear they're running between 30 and 35. I don't know if they can actually get 50, but there's information out there. I suggest you look into it. And then there's immersion cooling. And immersion cooling, there's two types of immersion cooling. So there's single phase. So single phase immersion cooling is exactly what it sounds like. It's a single phase. So if we think about phases of a material, organic material, if you just took water, for example, water is unique in so much as that it can have three phases. You can have the solid state, and then you can have a liquid state, and then you can have a vapor state. Whereas in this case, single phase immersion, they don't go through the second, or it goes from the liquid phase, and there is no vapor phase. It just stays in the liquid phase. And this is an example here of a type of, it's typically mineral oil, although 3M makes a great single phase product. I'm not exactly sure what the pricing is because we don't deal in single phase at all. But I do know they make a decent product. But most of the companies I've seen out there are using some type of mineral oil product. and they add some type of surfactants or something to it that enhance its thermal capabilities or what have you, or usability. But this is an example of one type of mineral oil. It has its place in the world, and we've seen some great single-phase systems, but there are some significant challenges, and like in any technology, but it's been around for quite a while, and there's been some success. This is mineral oil. As you can see, when you put your hand into it, it comes out, it's a little messy here. It doesn't exactly dry very easy, and as you can imagine, if you're dipping electronics in it, it can cause some challenges. One thing, if you're ever dealing with single-phase fluids, except for 3M, I think 3M makes a great product. It doesn't do this. It dries a lot like the two-phase products that we have, which is better, but it can be quite nasty. And you'll note that most of the single-phase applications supply you with an ample supply of these things. So, and it can be challenging to get off the electronics if you maybe need a vapor degreaser or some type of alcohol bath or something like that, which can be challenging for OEMs to take warranty things, whatever. But you can get some significant densities in there. They have their certainly great deployments are out there, but it's again not something that we deal with. So we'll put that aside. Two-phase liquid immersion cooling. So that's what we're here to talk about. So I wanted to give you the history, what's been done, what's being done, and where the future is, what we believe the future is, and that is two-phase liquid immersion cooling. So there's three key components to two-phase liquid immersion cooling. Not two, three. 2 phases, 3 components. There's the mechanical electrical, and it's the tank, it's the condenser coils, it's the liquid management, it's the vapor management, it's the controls around it, it's the security around it, and all those type of things. It's the actual physical unit itself. And so let's Drew, if you could show a picture of one of our Otto units, the Otto 120, that would be fantastic. So what you're looking at there, that is an Otto 120. That's 120 kilowatts of high performance computing in a box. It's basically a data center and a computer in a box. And what we do there is, that is what I'm calling it about, is with the 3 components to two-phase liquid immersion cooling, that is one of the 3 components. That is the data center, the cooling infrastructure, mechanical, electrical control, security, all of those types of things. Thank you, Drew. The other part of it is the dielectric fluid. I love the dielectric fluids. There's a number of great dielectric fluids out there on the market. We focus on 2 of them. We've done extensive testing with these fluids. One of the fluids, or a number of these fluids, are made by a company called 3M. I'm sure you've all heard of 3M. Great company. We have a great relationship with them. We've been doing development work with them for quite some time in our labs, in their labs. And it's great collaboration there. And there's a number of different types. There's Novak 7100, there's FC72, and they all have their place in the world. And they're great products. And unlike things like mineral oil and other things, when you put your electronics in there, they come out dry. And I'm going to give you show you an example of that in 2 seconds. So 3M, great product. Little bit pricey, but we're working with them, and supply and demand. So as the market increases for the demand of the two-phase immersion systems like Otto units, you'll see they'll go into production, they'll have more demand, and you'll see prices coming down. And we're negotiating great prices, and have negotiated great prices with a number of companies on the fluids. And you'll hear a lot about people talk about whether they're in other technologies, cooling technologies, or other people who are looking into this. Their concern is that these fluids can be quite expensive, and that makes the overall business case not so attractive. Well, one of the ways we've resolved that, and we have resolved that, is we've designed a system that is extremely economic. So the actual Otto, we talk about the three components. There's the Otto system itself, and we've made that extremely low cost, high efficiency, and very reliable. And so we've driven that cost far down. And in fact, I don't know if we have anybody from CBRE on the WebEx today, but great company, CBRE. We've been working with them for a number of years. We engaged with them to do a 10-year total cost of ownership, and looking at independently. We provided our information, And then they reached out to the other organizations to provide their information. They did it as an independent study. We will share that with all of you at your request, that 10-year total cost of ownership, which shows, traditional air-cooled stuff, 9 kW racks, rear-door heat exchanger, water, liquid on chip or water on chip, single phase and two phase, and other technologies, and really how, when the dust clears, from a total cost of ownership over 10 years, where that lands. And ultimately, we're about half the cost of all those other ones, 30% less in some cases, but in general, about 50% less. And that's because we were able to drive the economics through manufacturing with our partners at Jabil, phenomenal company manufacturing globally, our partners at Vertiv, wonderful company, great sales team, great engineers and manufacturing team, to be able to drive those costs down. So when we talk about fluids, getting back to fluids, we've offset the costs, and these costs will come down. I promise you that, because they're in the business of making sure that, one, we can drive a reduction in some of these, products that cause environmental impacts and things, and these things are great. And there's also discussions around the environmental impact, and we're going to address that in a second. So that's 3M. And then you have Solvay. Solvay is a fantastic company. We've been working with them for quite a while. This is not meant to be a commercial for these companies. I'm simply giving you an overview of two phases of immersion cooling and who's involved in the ecosystem. So we've been working very closely with Solvay. They make a number of products. This happens to be the HT55. It has what we call a flash point, or a vapor point of 55 degrees Celsius. And we'll talk about what that means in a minute. And so let me show you the difference between, say, and these are very similar, by the way, both from use case, and I think the Solvay might be a little bit less expensive, but I have faith in 3M. So we're going to show you a little bit here. It's always good to wear a little PPE, so I'm going to put my goggles on here, just protect my eyes. And I'm going to pour a little of this stuff here. I don't have enough of the 3M because we're using that back in facility. And I'm just going to pour it in here, very simply. And we're going to dispel a lot of myths about this stuff. There's people, oh, it's just going to evaporate and disappear, and you're going to lose all your money, and then you're going to have to refill it all the time, and all. And listen, we use this stuff probably more than anybody. We've handled more of this fluid than probably anybody on the planet over the last number of years. And we love this stuff. And so one of the things that's really great about it is it's perfectly clear. As you can see, you get a little light here. I don't know if you can see it. You can see through that. Perfectly clear. And it is heavy, though. It's about 14 pounds a gallon. It's about 1.8 specific gravity. So it's about 14 pounds a gallon. It's heavier than water. So it's heavy. But it's just how beautiful and dense it is. So here's my phone. I'm going to take the case off because I'm just going to pull the phone out a second here. This is my brand new iPhone. Well, relatively brand new. I'm not even sure what it is, but it's relatively new. And I'm going to show you something here, assuming I can unlock it, and how awesome this stuff is. So I'm going to do, as a matter of fact, I'm going to do a little TMGcore video. Let's just do that and show you. There we go. So here's a little video. You can see my phone is playing now, and I'm just going to throw that right inside there. And there you go. Can you see that okay? Good. So you got the video playing. Yeah, perfect. I'm just going to let that play for a little while. And so what I'm trying to show is it's dielectric in nature, which means it doesn't conduct electricity, like the mineral oils and like distilled water in some cases, or reverse osmosis, but that can reconstitute. This stuff is bulletproof. It's extremely inert and very, very safe. The MSDS sheets for these fluids is comically innocuous. If you consume it, if you ingest it, stop ingesting it. If you don't feel good, go to the doctor, but you're not going to die. I assume don't drink gallons of it, right? You can put your hand in it like I just did here. And one of the beautiful things is, like right now, it's about 2 seconds, 3 seconds, and it's dry. And it's clean. Now, I don't suggest you do that all the time. You should probably wear gloves because guess what? It dries out, and you need moisturizer. So my hands are getting old enough as it is. I don't want to do that all the time. So I suggest you wear gloves, but you don't. For purposes of demonstration, you don't need to. So there's my phone right there. It's still in there doing its thing. I'll take it out for a second and just kind of shake it off real quick. And so one of the ways that we protect the system is through the vapor management, which I talked about. Now it's completely dry. It's completely dry. There's no slipperiness to it. My phone is actually nice and clean and clear. It's cleaner than it was when it went in there. Doesn't have any, if it had any potential coronavirus in there, it's probably gone now. I'm not saying you should use it for that reason, but because I don't know, but it's very clean. I'm going to go ahead and start the video up again, put it back in there to show you. So it's very safe stuff. So people talk a lot about cost. Okay, so we talked about the cost and how we offset that. They also talk about it likes to disappear. Well, yeah, under certain circumstances. It's heavier than air. It just likes to sit. Unless you have a fan blowing across it, you're not going to get a lot of loss here. But you have a fan blowing across it or something like that. Eventually, if you left this out, I would say probably 3 weeks, it would be probably evaporated. Just from what our experience is, and we've had a lot of experience playing with this stuff, thousands of gallons of this stuff. So we've seen it over the years, and so it's stable, it's very stable stuff. In some cases, they use this to put fires out, so it has no flash point, and again, very inert. Whereas like minerals and things like that for single phase, they have flash points, and you need typically you need some secondary, not always, but some secondary fire suppression systems. With this stuff, it's just not necessary. In fact, I think 3M makes a great Novak fire product that's very similar to this in nature. Anyways, so there you go. It's running. My phone's still running, and it will run forever in clean environment. So one of the ways we prevent the concern about fluid loss because of the price is in our systems, by the way, and two-phase liquid immersion cooling are not pressure vessels. They're not ASME stamped pressure or vacuum vessels. So low cost. You don't have to worry about getting all the stamps and certifications and things like that because we run at atmospheric pressure. And we control the entire system at atmospheric. All our systems are fully redundant as well. So we use, we call it fault tolerant design methods so that all of the systems can be operating. You have one pump fail or power system fail or whatever, and the system still maintains itself and it still operates, and it can be maintained while it's operating. So you don't have to shut it down. So for N+1, N+2, N+3 configurations, military applications, and so on, two-phase immersion cooling through the Otto platform is phenomenal for that because you have that security backup. And so, but one of the ways, how do we do this? So in general, how does two-phase liquid immersion cooling work? So you have the fluids, right? You have the box itself, and then you have the hardware. So we'll talk about the hardware in a minute. So backing up, the fluids go inside the tank. And so Drew, if you could pull up a picture of the actual process. This is an example of of our process. There you go. So the Otto two-phase liquid immersion system. Now, this doesn't have to be the Otto system. This is not meant to be an Otto commercial. This is about two-phase liquid immersion cooling. So if you look in diagram 1, just imagine that's a tank, X brand. And the yellow in there are the actual servers. Those are the blades, the 1U blades, whether it's our blade or Dell's blade or Intel or Supermicro or HP or whomever. And Inspur, for that matter, great company. You put them into the tank. And again, the tank is sealed, however, it is not pressurized. And it doesn't run under a vacuum. It's just atmospheric. And then you pour the fluid in, you would what we call charge the system. You put the fluid in there. And then, and because all of our, in our case, auto-ready servers, all of the power supply, A+B, redundant power supply, is on the back plane, and as well as all of the communications, where we can get up to 8 100 gigabyte InfiniBand connections or Ethernet connections on the back. So a lot of connectivity on the back. So you don't need an operator to slide it in, because we also use a robotic system, which we'll show you in a second. But it sits in that tank in the bath of the dielectric fluid, whether it's 3M or Solvay or other. And then you put your software stack on there and you start running your workloads. And those chips heat up, as you see in diagram 3. The heat gets pushed into the chips. The chips then give off their heat into the boiler plate, which I'm going to show you as soon as that slides off. And then that transmits to what we call the latent heat vaporization, but you hit the thermal saturation point of the fluid, and then that fluid then turns into a gas, bubbles up, and then turns into a vapor. And that vapor then goes into what we call the head space. And that head space is where what we call the cooling coils are located. And I have an example here I'll show you in a second. And then we circulate water through the cooling coil, which absorbs that heat from the vapor, and then that vapor collapses back to liquid, and it just goes on and on and on forever. So, okay, well, how do you maintain it? You say, okay, well, if it's not a pressurized or closed system, and you get vapor in there, when you open up the system to operate it, to let the robot pull out the blades and replace it, because it does its self-healing system, doesn't that vapor just disappear into space? Well, normally, yes, you would do that. It would. However, we came up with a really cool process over the last couple of years of development, whereby we can prevent that from happening. And I'm going to talk to you about one of the ways we do that. So, backing up. So this is a small coil, what we call a condensing coil, that sits up above the tank in the vapor space. This is made of copper, brass and copper combination. This happens to be a Wieland. We love Wieland. They're made in Germany. But they spiral barrels and gives great heat transfer, because you increase the surface area, like what we're doing with the boiler plates that I'm going to show you in a second. And then you supply warm water. It's actually hot water, warm water, whatever you define as hot or warm. 90-degree F water in, so it's not chilled water. And then we push it through the different coils, as you can see here. And then it gets removed. We take it to a secondary final heat rejection, which is a closed loop system. Can be either, and it doesn't have to be water, by the way. It can be a refrigerant. It could be whatever it is, a medium, cooling medium you want to use. Water is cheap for most cases. You add a surfactant so that it doesn't scale up and things like that inside. And you get heat degradation or heat transfer loss, because you get scaling or whatever from the water, minerals in the water. So we add surfactants, detergents, and so on. And it's a closed loop system. Or you could use a dry cooler, which actually doesn't use water at all. And that is your secondary, basically your final heat rejection. Or a cooling tower, a very high efficiency, closed loop heat cooling tower or something like that. It just depends on how big the unit it is, depends on how big the final heat rejection is. But these are the cooling coils that go inside, that collapses the vapor, that turns it back into a liquid as part of the two-phase. Liquid phase, vapor phase, liquid phase, vapor phase, and it just goes on and on forever. So when you open up that hatch and you're removing one of the blades, we increase the flow, and we modify things so that we drop that and collapse that vapor down to about 99.98%. So there's a tiny amount of vapor left up there, which constitutes a very, very, very small amount. Now we're almost to the point where we can get 100%, and we're working on that and dialing that in. We also don't allow air in it. We have something called capacitive membrane. And it all sounds complicated. It's not complicated. It's actually just a sophisticated system. We tried to keep it, and we have kept it very, very simple. From the physics perspective, it's a very simple process. We've just made it a bit more sophisticated for commercial applications for the end users. So we're able to guarantee through our two-phase system no more than 1% fluid loss per year. And it comes with a 10% buffer when it's charged and distributed to the client or to whatever deployment, whether it's a decentralized distributed point of presence network where you could have thousands of these micro data centers spread out across the United States or the globe for that matter, and controlling it from a centralized NOC. Or if you had a hyperscale with the Otto 600s, we have an Otto 600 unit, which is just 600 kilowatts. We use kilowatts in this business, in the cooling business, because how many watts are we trying to cool? Versus like petaflops or hexaflops when you're talking about the end user when they're dealing with actually workloads. So we're able to keep an atmospheric system and allow for operators and owners of this technology, two-phase immersion cooling technology, to operate for 10 years without adding any fluids. That's pretty awesome. So and we fully guarantee that it's a total turnkey solution. We provide the fluids and the service, the whole ecosystem associated with it. So that's the overall on the fluid side of things. going now towards the hardware. So you have the infrastructure, you have the Otto units themselves, the mechanical, electrical, the stuff that the vapor management that allows the absorption, desorption to prevent any pressure as the vapor increases in the tank. We absorb that through activated carbon, and then we desorb that, so you never get a pressure increase. So it's very safe. We have, again, we've done full FMEAs to show that we have backups on backups, and so it operates at atmospheric in a very safe and effective manner. And then you've got the fluids. We talked about the fluids, the costs associated with them, how they work. Different fluids work for different things. In some cases, fluids can interfere with optical interfaces, and so air gapping and things like that, where you can get distortion. Other fluids, because of the dielectric constant, don't do that. So, and we're working very closely, as are others, because there's other great companies out there, to develop components that don't have air gaps, that are sealed systems, so that we can use a broader array of fluids that don't have that impact. And it also helps drive down the cost. So some of the fluids that do have dielectric constants that do impact the optical interfaces are cheaper. So again, driving down the cost. So then there's the hardware. So we talked about fluids, we talked about the units themselves, and then there's the hardware. So you got to have something that can go into the fluids, right? Now, as you can see, my phone isn't auto ready. It just goes into there, and it's been sitting in there for I don't know how long. But it's off the shelf. And like a lot of single phase stuff, you just take stuff off the shelf and you put it into the fluid. You're limited as to densities. There's a certain limit to the amount of heat that you can disperse efficiently in single phase without having to really drop the temperatures down and cool more or whatever. Whereas two phase, they have a higher heat tolerance or absorption. You can go up to 50 in some cases with the boiler plates, which are these things, which sit, as you can, there's already our boiler plates on here. These are the CPUs, these are the GPUs. We designed these ourselves, which uses a copper silver nitrate mixture. We worked very closely with 3M on developing this, and thanks to Phil Tuma and Steve and the other people in Phil's labs at 3M. Kudos, you guys, awesome job. Kudos to Kinney Industries, who've been working closely with us to help develop these technologies to allow for incredible heat transfer capability. So we're able to, in some of these cases, we're able to get close to 60 watts per cubic centimeter of heat transfer, which is incredible, by the way. So what you do is, but you have to have things that are really designed to make it valuable for two-phase immersion cooling. If you're looking at light loads, non-high performance computing, things that aren't extremely dense, then two-phase immersion cooling isn't. It just isn't. You're better off going with a traditional rack, a rear door heat exchanger, water on chip, or even single phase for that matter, because single phase fluids are really expensive. But again, you have limitations for density. So what we're focused on two-phase immersion cooling is the future of high density computing. Really high dense compute loads, AI, machine learning, 5G networking, where you've got 128 frames per second for say cloud gaming, for esports applications, autonomous driving vehicles, where you get really low latency stuff, high performance computing. That's two-phase immersion cooling, and that's what we're focused on. So that other stuff there's great products for those other types of applications. That's not for two-phase immersion cooling. So just to make that clear. But you also, so for that case, we want to make things really, really, really dense to make the value proposition right. So if we can get, in this case here, this is what we call the G1611. This is a 6,000 watt 1U server that we can overclock to 7,300 watts. And look at our chip temperatures of GPU chip temperatures. I think we have 16 NVIDIA Tesla V100 GPUs in this 1U server with 2 Xenon Intel CPUs. And we can overclock this at 7,300 watts, and the chip temperatures are about 82 degrees Celsius, which is below what it's rated to run in air. So we're able to get extremely high densities, and all of a sudden you've got a lot of compute in a very small space, and it makes the value proposition there. And the more the industry works towards that, the more sense this all makes and will continue to make. So you're making auto-ready stuff. So there's the hardware, and we're working very closely with companies like Dell and Intel and Supermicro and Inspur and a number of other companies to develop what we call the auto-ready form factor, which is a chassis. They all look similar to this. They're designed to be robotically hot swapped and allow for immersion. You see there's a bunch of holes in here. So this is by design, that's engineered specifically to allow for the bubbles, the vapor to come out of the liquid solution and exit the tank into the vapor space. And so all of this was thoughtfully done. All of the interconnectivity for InfiniBand or other Ethernet is on the back, the up to 8 100 gigabyte connections here, and also the 2 redundant A+B power feeds that feed this at 12 volt DC, or you could feed this 48 volt DC, or you could actually run this on AC if you want to. It just depends on what the use application is. But so we could take that. This is what this is. This is actually an auto-ready chassis. And you can tell there's nothing else in there. We did this by design so you could see this is the Dell Intel stuff right here. All this wonderful stuff. Everything else is what makes it auto-ready, which will go in there after the fact. And we can do this for any product. We can put a storage system in here. We can put CPU heavy, GPU heavy. Doesn't make a difference. So hardware is key. So two-phase liquid immersion cooling as a overall high level, you need to have the infrastructure of the auto units themselves, electrical, mechanical, security, control software, interface, so you can control it remotely or locally through the HMI. And you need the fluids, these great fluids from these great companies like 3M and Solvay. And you also need to have the hardware. We've developed the hardware. So we don't develop the fluids. We have great companies who do that. We help develop this stuff. So the servers, the auto-ready servers with companies like Intel and Dell and others, and Supermicro and others. And then we also develop the cooling, what we call the plates and things like that go as part of the hardware, and then the auto units themselves. So we focus on the hardware and the auto units, the material suppliers, the manufacturers like Jabil and Vertiv, great companies who are manufacturing these things for us. There's the actual auto units themselves. It's making sure that they're QA'd and QC'd and they're reliable and they're manufactured properly and release tested. There's all of the warranties that come along with it. All of these things are key, things that we've developed, and so things you should ask. So if you're interested in two-phase liquid immersion cooling as a infrastructure, which I highly recommend you look into it, you need to be asking those questions. The fluid suppliers, do you have enough fluid supply? Do you have immersion-ready hardware? Do you have a Dell offering for the auto-ready servers? Do you have an HP offering? Do you have a Supermicro offering? Do you have an other, whatever? And what are your options? And then, do you have any service, turnkey service offerings? What is it? Do you have like 4-hour on-call emergency service? Do you have 24/7, phone service? How many technicians do you have in your region, locally, globally, regionally, whatever, to make sure that they can be on site to support? Do you have training for the operators and others to ensure that if you're running the systems yourself, are your operators trained on how to use this? All of those things I can say yes to. Some of the things we're finalizing now, but in two-phase liquid immersion cooling, because it is the future of high-performance computing and allow for small micro data centers on the edge, like our podcast called The Edge. We see that going in that direction, and we're completely focused in supporting that industry and that vision. You need to be able to ask those questions. So all these things are critical to ensuring any evolutionary technology is ready for prime time. So we here at TMGcore are dedicated to all of you, our customers, our partners, what we call our auto-ready channel partners, our suppliers. We're here to support you the way you're here to support and have been supporting us for so long. We're very excited to be working in this industry. We feel blessed. We are extremely transparent at what we're doing. We know there's a lot of great technologies out there. This is one of them. And there will be those who adopt it and those who don't. Again, it's a very specific type of use case. We feel it's important to educate all of you and the world on those who are in this industry and those who use this technology on what their options are. And we've got a great team. Ashley Panfil, who's our global head, or senior executive vice president for sales. She's always, she and her team are available for, you can contact them at any time via LinkedIn or email directly to TMGcore, ashley.panfil@tmgcore.com, and to come in, visit us. As soon as this thing kind of blows over, ideally in the next few weeks or a month, we'd love to have you out to the facility. Come into our labs, come see our auto units. We are launching a really exciting thing. This is a little bit, I'm going to admit it, this is a pitch or a plug, as it were. So we're launching something called the Auto Ready Experience. And this is it's part reality and part virtual. And we wanted the reality to really stand out. And it's called the Auto Remote Experience. And what that does is it allows for people remotely to, with our permission and given the credentials to log in into an interface, a web-based interface, to actually connect to an auto in our facility and cycle the robot back and forth, to hot swap blades, to actually run one of our G16s and 11s or our Dell C4140. We're coming out with a brand new Dell, which is about it's going to be about 4,600 watts or more in a 1U form factor. We're working with Supermicro right now. You'll be able to test all these blades in the auto real time, upload your software stack, run all your workloads, do baseline testing, overclock it, push it, try to break it, and enjoy it, and figure out and imagine what you can do. And working with your, if you're a Dell rep or an Intel rep, or if you're an HP rep or a Supermicro rep, whoever your sales rep is, whoever you prefer to have in your data center, or if you're exploring new ideas, try out a server, run your workloads, whether you're in academia, or if you're in the healthcare industry, or if you're in the finance industry, or oil and gas, or esports, or whatever you're in. Each of these segments, educational, you'll be able to jump on. It launches the first week of June. You'll all be contacted. We'll let you know. You can talk to your IT specialist if you want to participate, and it's free. It's completely free, and you'll get time, and you can work and put your workloads on the most powerful blades in the world and manipulate it, run and operate, and have your operators run a dozen Auto 600s or 120s, spread them out on a map, look at real-time video of the things working back and forth. So it's really exciting. And the one thing I want to leave you with, if you could show the last video we'll show, and then we'll wrap it up. If you could show the video of the Auto 120 operating, this is this type of live feeds you'll be able to see when you're working and operating what we call the Auto Remote Experience. We highly recommend you reach out, you sign up for it, and you enjoy it, because it'll give you an opportunity to see what two-phase liquid immersion cooling is up front and live, and operate an actual physical Auto 120 unit from anywhere in the world, and get your team and get yourself acclimated to the technology. You'll be getting real-time feedback, telemetry on chip performance and temperatures and all those types of things. So I think, there we go. There's the video. You should be able to see it now. A little bit of latency there because I don't think we're running on an auto right now. But normally you wouldn't see those cables and things like that. It would be completely you'd see a white thing. But we've got some testing on. That's an Auto 120 right there in our facility. But you'll be able to operate this remotely. So with that said, thank you very much, everyone. So happy that you were able to join us. We don't have time for questions right now. Well, we might have time for 3 minutes. We might have time for one question. Drew, do we have any questions?
Yeah, we had one question, was where did the name Otto come from?
Well, that's a great question. It was a code name because we developed the technology in stealth mode because we were filing IP patents and all that stuff. And we didn't come out to the world until the November 18th at the Supercompute Show in Colorado, where we brought the Otto unit there. Some of you may have been there or even participated. But we call it Project Otto so that we kept it silent. And it was actually Taylor Monig, who's our chief operating officer for the company. I think he's one of the youngest chief operating officers that are out there. I think he's like 27 years old, but he's a brilliant young man. And I think it was named after a cartoon. And we're like, yeah, we'll just call it Project Otto. We have another project going on called Project Ephesus, which I can't talk about right now, but we'll unveil at some point. But that's how the name came. And then we just kind of embraced it and said, hey, that's a cool name. It looks nice. Our Ottos actually look like OTTO in a way, and we coined it to say, as an acronym, over-the-top operations. So, and it's a coin on the phrase automatic because we do have a robotic system that hot swaps the blades. Again, come down and check us out.
Yeah, a couple more real quick ones. For two-phase cooling, do we have to filter the liquid, the fluid?
Yes, we recommend you do. You don't have to, but we recommend you do. And the reason for that is because a lot of the stuff that you get right from the factory, like blades right from the factory, have solder flux. They have packing stuck materials in there, human hair, whatever, right? Things that you come out. It's not a sterile environment. So because our systems in the fluids are so great at cleaning things, as you can see, my phone is spotless, hasn't been this clean since ever. It removes all of that stuff. And so what you don't want to do is have that stuff floating around because it can degrade over time and prevent the wonderful, applications, the heat transfer capabilities. So yes, we filter it, and our systems are all filtered. If you ever come across another system that isn't, don't buy it. You want to have it filtered. It's very easy to use. You can swap out the filters. They last years. They're cheap, activated carbon aluminum filters. Yeah.
Perfect. And one last one. Can you speak very briefly to the cost differentiation between two-phase and single-phase fluids? Not with specifics, but at a high level.
Yeah. So some of the biggest concerns, again, we're all about the fluids, right? Our systems, I don't know. I haven't gone out and priced single-phase systems directly in a long time. I know they're getting lower costs. They're a lot less complex. Or say sophisticated, not complex, sophisticated. They're not using robotic systems. So you can get some great single phase products that do for your, again, it's specific to your workload, that do great things for a particular application. When you need high density, high performance compute, lights out applications in mini data centers, things like that, you're gonna wanna go with a two-phase immersion system like an Otto. But from a pricing perspective, right now, according to and we'll share the total cost of ownership, we're roughly half the cost, or maybe 30% or something like that. I'll have to double check. I know they're driving their costs down. One of the biggest things is their fluid costs is a lot less, which is why it was so important for us to develop a system that basically eliminated fluid loss. And so that helps. It's initial cost, but then it's amortized over 10 years. But right now, just based on the total cost of ownership that CBRE did, I believe we're between 30 and 50% less than, say, two-phase, single-phase immersion.
Perfect. And we are at we've at the top of the hour, technically the bottom of the hour. One last question that I know you can answer very briefly is: do we have to turn off a tank to remove or substitute one server or system? No,
we do not actually. And here's what I recommend. I recommend you go to YouTube right now while it's fresh in your mind. And just go to TMGcore, and there's a video in there. I believe I forget what it's called. I think it's called Hot Swap or something like that. It shows you how we do it robotically. So what happens is through the HMI or remotely, you literally, and you can set it up so that the software recognizes degradation and performance of the server all on its own, and you can set the parameter. The customer can set the parameter, and the robotic system. It's a high cycle use industrial robot, so millions of cycles, so it very rarely needs any maintenance. We have a standby rack that allows for the servers that we have three, with the 120, we have 2 standby servers and 1 space for a replacement server. So 2 standby servers, the robotic system through the software platform, or if you want to override that and do it manually, you can operate the robot, and you'll be able to do this from the Otto remote experience coming in June, and do it for yourself. The robot will actually remove that server that's failed. The hatch opens automatically. It'll remove, the robot will snap into the top of this, pull this up out of the tank, slide it over, drop it into the standby, what we call magazine, and then it'll move over, pick another one of these up, slide it back, slap it into any slot in the rack. An Otto 60 has 10 slots. An Otto 120 has 20 slots, and an Otto 600 has 100 of those. So a lot of blades, up to 6,000 watts each. And so you don't need an operator to do any of the swapping, and it does it automatically.
Perfect. All right. Well, that's all the questions that we have. And again, everyone, thank you so much for joining this webinar masterclass presentation. JD, thank you so much for your time and all of the wonderful information you presented. To everyone's questions, we'll also reach out with some of the information that JD mentioned, the TCO. If you have any other questions, please reach out to us directly. You can reach out at info@tmgcore.com. And for sure, make sure and check out our YouTube channel for other information and things of that nature. And we look forward to chatting with you all very soon. And we hope you stay safe, and we'll chat with you soon. Thanks.
Bye, guys.
Hey guys, Drew here again. Thanks so much for taking the time to watch our masterclass on two-phase liquid immersion cooling. We hope that this content was both educational and informative. In the event that you have any questions about the material that JD covered in this masterclass, please feel free to reach out directly to us, and we'll respond as soon as we can. If you're watching this on YouTube, feel free to drop the questions in the comment section below. And if you received this masterclass recording from someone at the TMGcore team, feel free to reach out directly to that individual, or you can email us at info@tmgcore.com. Thanks so much. We'll chat with you soon. And remember, the edge will go as far as you take it.